Okay, welcome back, students. Let's jump into chapter 8 and cover 8.1, the general theory for linear differential equations. Okay, okay, 8.1. General theory for linear differential equations. Definition. Okay, general linear differential operator of order n is written as L equals d to the nth power plus a1 d to the n minus 1th power plus a n minus 1 times d plus a n, defined by Ly is equal to y to the nth derivative plus a1 y to the n minus 1th derivative plus a n times y prime plus, sorry, that's a n minus 1 plus a n y. Okay, number one, determine the kernel of the linear differential operator uh, L, yes, L is equal to d minus 2x. Okay. Given L, y equals 0. Okay, so what was the original differential equation? The original differential equation would have been, so d minus 2x, okay, d would have been, so a n minus 1 would have been 1. A n minus 1 is 1, and then a n is 2x, or minus 2x. Okay. So this would be 1 y prime, y prime minus, okay, minus negative 2x y, okay, minus 2xy is equal to 0. So that would have been my original linear differential equation. Okay, so we can solve this linear differential equation. We want all the values that will make this 0. Okay, equal to 0. That would give me the kernel. Okay, so what are all the values that are going to make the 0? Well, let's just solve. Okay, so this is my integration factor is going to be e to the integral of negative 2x dx. Okay, so this is going to be equal to e to the negative x squared. Okay, and so I can take that e to the negative x squared and I can multiply it through. And 0. Okay, and so I get e to the negative x squared y prime plus 2x e to the negative x squared y is equal to 0. Okay, so I'm gonna again undo the product rule here. So this is e to the negative x squared y, okay, d dx, okay, is equal to 0, right? So 0. Now I can integrate. So this is going to be e to the negative x squared y is equal to c. Okay, and so I could then divide by negative x squared or multiply by e to the negative or e to the positive x squared. So maybe I'll just do that. E to the positive x squared, e to the positive x squared. That's going to cancel that one because it's going to end up adding to 0, and then it's just going to be 1, and 1 minus 1 times y is 1. So y is equal to c e to the x squared. Okay, so that's my solution to the homogeneous differential equation, homogeneous linear differential equation. And so we're going to write that as our kernel. So the kernel of L is equal to c e to the x squared, okay, where c is an element of the real numbers. Okay, let's go over a definition here. Definition, consider the nth order general linear differential equation okay, a naught x y to the nth derivative plus a1 of x y to the n-1th derivative n minus 1th derivative plus dot 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 plus a n minus 1 times y prime of x, okay, y prime, okay, plus a sub n is equal to f of x, okay, or expressed as Ly is equal to, I think that's a sub y, is equal to f of x. Okay. Okay, if f of x equals 0, okay, if f of x equals 0, then we say L sub y equal to 0, is called homogeneous. And if f sub x is not equal to 0, then L sub y is called non-homogeneous. Okay, another definition. Different equation is said to be regular if on an interval I, the coefficient functions are all continuous of the coefficient functions and f of x, anything that involves x basically, and f of x are all continuous functions on I. Okay, theorem. If an nth degree linear differential equation has n initial values then it has a unique solution. Okay, that is, for example, okay, if I'm given y prime plus y equals 0 and y naught equals -2, okay, then that's going to have a unique solution. Okay, first derivative, one initial condition. If I've got a second derivative, I would need two initial conditions. I would need to know what's happening at y and what's happening at y prime. Okay. So if I have a single differential equation with a single derivative, then I only need one initial condition or initial value. Okay, if I have two, I would need two. So one, I'll just put IV initial value, and then this is two initial values. Okay, theorem. Okay. Of all solutions to the nth degree homogeneous linear differential equation y nth derivative plus a1 x y to the n minus first derivative plus dot 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 a n minus 1 of x y prime plus a n equals 0. Oh, a n of x, sorry, equals 0. Okay, homogeneous. Okay, is a vector space of dimension n also these solutions okay, which we'll call y1 y2 dot 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 to yn, okay, form a basis for the differential equation if they are linearly independent okay, and can be expressed as equal to c1 times y1 of x plus c2 times y2 of x plus dot 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 plus cn minus 1 y n minus 1 of x plus cn y of y n of x. And this is referred to as the general solution to the differential equation. So all A1 is doing is kind of setting up what we're going to be talking about over the next chapter. Okay, getting all of the terminology down, getting the idea that we're going to have this value D and how that works. Okay, that variable capital D. So let's get a little bit more familiar with this idea. Okay, and let's do an example. Number 2 here. Okay, determine all the solutions to y double prime minus 2y prime minus 15y equals 0. So we've got a second order differential equation. It's homogeneous, and each of the functions in front of it are just variables. Just constants. They don't even contain any x value, any x variables. So I could put a 1 in front of that, and that will give me my coefficients. Okay. The solutions to this, okay, solutions to this differential equation are of the form y equals e to the rx, where r is a constant, okay, find the general solution. Okay, so find the general solution to this differential equation. Okay, so they're all going to be in that form. So the idea is that we're going to take D, to go back to the definition here of what D is. Okay, it says, okay, let's go way back. Okay. It says I'm gonna highlight this. General linear differential operator of order n is written as L equals D to the nth power A1, D to the n minus 1, A plus dot 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 all the way to an minus 1 D plus an. And so the derivative, what we're doing is we're taking the derivative and say like y to the n is the third derivative. We're taking that and we're replacing it with this variable d to the third power. So we're taking a derivative and we're changing it into a power is really what we're doing here. So these two correspond to each other. Okay. So d to the nth. So this guy here, okay, and this guy here correspond to each other. So it's saying, look, I have y to the nth derivative is d to the nth power. Okay, and then a1, that's just the coefficient, and then y to the n minus 1th derivative, and d to the n minus 1th power. Okay, so what we're doing is we're just taking these derivatives and we're turning them into powers, and we're using this operator d to help us do that. Okay, this variable d. So let's look at this guy. So I've got y prime with 1 in front, which is what I want. I want the 1 in front. Okay. And so that y double prime, that's y to the second derivative. I'm going to replace that with d squared. So that becomes d squared. Okay, and then minus 2d minus 15 is equal to 0. Okay. Okay, and what I can do is I can factor this thing. Okay, and this becomes d minus 5, and d minus, or d plus 2 is equal to 0. And so I get d equals 5, okay, and d equals -2, okay. And so the idea is that the solutions have this form here, right? So let's work with that real quick and see how these d's correspond to these guys over here. Okay, how's that going to help us? Well, if we take y, okay, and we know that it's e to the negative rx is the form of this solution, then we take the y prime, that becomes r e to the rx, and then y double prime is going to be r squared e to the rx, right? And so see how this works. If I plug these back in, I get into my original differential equation, I get y double prime, okay, minus 2 times y prime minus 15y is equal to 0. And so I would get r squared e to the rx minus 2 r e to the rx minus 15 e to the rx is equal to 0. Now let's factor out that e to the rx. And what we get is we get r squared minus 2r minus 15, which is, okay, the same thing that we factored if we when we use the d's. Okay, and so this ends up being r minus 5 times r minus r plus 2, and so we get e to the rx, okay, times that. I'll just put it up here, okay, is equal to 0. Now if I divide by e to the rx, okay, it still becomes 0. So the only thing that matters here is the r minus 5 and the r plus 2. So we're kind of like doing a fast track on this process by using the d's. We just say, well, we're gonna end up with this thing e to the rx on the outside. It's gonna go away, and so the powers, okay, really, because of the form of the solution, you know, the form of the solution is y equals e to the rx. And so if we say that, oh, r is equal to 5 or r is equal to -2, then we have, you know, the solutions to this differential equation would take some sort of linear combination of e to the 5x and e to the -2x, okay? So I don't know how many of each. So what I can do is I can say, well, y equals c1 e to the 5x plus c2 e to the negative. Oh, you know what? This isn't 2. This is 3. I'm kind of screwed up on my factoring. That's okay. This is -3. Okay, this is 3. And this is -3. And so this would be -3, e to the -3x. Okay, go back over here. There we go. Okay. And there's your solution, your general solution. This is a general solution. Now, if I was given initial conditions, okay, I could easily find what C1 and C2 are, okay? In this case, I was given a second derivative, so I would need two conditions. For example, if we said y naught is equal to 1 and y prime of naught is equal to 2, could we find a particular solution here? And yeah, we could. We just plug this in. Y equals, okay, c1 e to the 5 times 0, okay, plus c2 e to the -3 times 0. Okay, this is gonna go to 1. This is gonna go to 1, and so I just am left with c1 plus c2 is equal to 1. Okay, that would be my first equation. If I took the derivative of the answer here, I would get 5c1 e to the 5x plus 5c2, or sorry, minus 3c2 minus 3c2 e to the negative 3x. Okay, that I would just differentiate that. And so then if I plug in zeros, that goes away, and that would be equal to 2. So we get 5c1 minus 3c2 is equal to 2. Okay, evaluating that at 0. And so I could use this system of equations. C1 plus C2 is equal to 1. I could multiply through by, say, negative 5. Negative 5, negative 5, negative 5. And I would end up with 2C2 is equal to negative 3. Divide by 2. And we get C2 to equal negative 3 halves. And then if we plug back in, C1 and C2 have to add up to 1. So okay, C1 plus C2 equal to 1. So C1 plus negative 3 halves equals 1. Add 3 halves to both sides, and I would get 5 halves. So C1 would equal 5 halves. Okay, and so my particular solution would be y is equal to 5 halves e to the 5x minus 3 halves e to the negative 3x. That would be my particular solution. Okay. Okay, that's 8.1. I'll see you in the next video.